Hi, everybody. I'm Kat Allman with the Open Source Programs Office, and it's my great pleasure today to introduce an old friend, Dr. Christopher Thorpe of Harvard University. Chris has been involved in computer science for quite a while now, including Yahoo and Tell.me, done some interesting things, some of which he's going to tell us about today. Thanks for coming. Take it away, Chris.
Thank you. Thanks, Kat. So I want to tell you about cryptography that is beyond the kind of cryptography that people usually think about, which is how do I keep my credit card number safe when I give it to Google Checkout on the way, right? How does someone sniffing my packets on the way, or someone hacks the merchant. Obviously, they're not going to hack Google, but they hack the merchant that gets the credit card number later on and comes back, and how do we encrypt that information? That's not what I'm going to talk about today. I'm going to talk about some advances in cryptography that have happened more recently than the kind of 1970s era crypto that most people know about, which are kind of like magic if you've never heard of them. I'm going to delve right into that. Let's think about an encryption function, E. And our encryption function will take some value we want to encrypt, call it a message M. And this is going to yield a ciphertext, C. So think about RSA encryption. How many of you have heard of RSA? Great. So you all know about RSA. What does RSA do? Anybody know? Can anybody tell me what the RSA function is? Modular exponentiation. Good. So modular exponentiation means that we're going to take the message M, raise it to a power E, modulo some number, which we call capital N. And when we do this, it becomes encrypted unless you know the factorization of N. Typically N, so this is our encryption function. An encryption function of M is M to the E mod N, and N is the product of two large prime numbers, P times Q, we'll call them just for tradition's sake. It has been shown, yes? Please zoom in on the whiteboard. Is that what you want? Wave at us if that's what you'd like to see. All right. You want to see more of the whiteboard. I will try to write bigger. There we go. OK. So that's good. How's that? OK. So for our television audiences. All right. Good. So this is not Einstein. This is RSA encryption right now. But we're going to get back into we will see, actually, I can do this, which looks more like Einstein, but it is an Einstein, and we'll show you what it means in a few minutes. So modular exponentiation means that I can encrypt things, and the RSA problem is the assumption that if I cannot factor N, I can't break this encryption. And one of my advisors, Michael Rabin, showed, in fact, that there's a similar function to the RSA function where E is 2, where you take a number, you square it modulo N, and being able to decrypt is equivalent to knowing the factorization of N. So because it's not known whether you can factor large composites efficiently, we believe this to be a strong encryption function. Now, I want to talk about a problem with RSA. Imagine I'm going to encrypt all of your social security numbers using the RSA function in my secure database. Anybody see a problem with that? Somebody captures my laptop with all your social security numbers encrypted with the RSA function, what happens if the laptop is stolen? Yeah?
You can run through all 10 billion possible social security numbers and get a match.
OK, precisely. So his answer, what's your name? Yasha. Yasha says you can run through all 10 billion social security numbers, do the modular exponentiation function, and because this is a deterministic encryption function, I can deduce everybody's social security number from the encrypted value on the laptop. So this is why RSA might be secure for, say, establishing a key a symmetric key that might be used for encrypting a connection in SSL, but is not suitable for direct encryption of private data. So getting back to Einstein for a second, what happens if I put this 2 there? What do I end up with? So if my message is m to the e mod n, and now I have m to the e squared mod n, this is m squared to the e mod n, right? My exponentiation is commutative. I know you're a mathematician, right? Is that right? So, so what I've ended up with is an encryption of the square of my message. Now, it turns out that can be interesting, but there's a lot more than that. And we'll refer to this as malleability. I can take an encrypted value and I can massage it into another valid encrypted value. So if I take this, exponentiate it to something else, I get something that I can decrypt by decrypting from RSA, right? So, all right, what is the first problem we're trying to solve? The first problem is this problem that I'm going to call semantic security. Actually, I didn't call it that. I think Goldwasser and Macaulay and some of their friends called it this. But semantic security is if I have an encryption of M1 and an encryption of M2, I can't tell, given these two values, whether M1 is equal to M2 or not. RSA doesn't stand up to this, and this is why the Social Security number attack holds. So what I do is I'm going to use a different type of cryptographic function that now, instead of encrypting just a message, I'm going to encrypt a message. So I'm going to throw away these old encryption functions, and now I'm going to make a new encryption function that takes a message and a random help value R. And this encryption function gives me a ciphertext that is dependent on the plain text message M and this random help value, so that if I see two ciphertexts, let's say I encrypt message M0 with R1, oh, let's say R0, and encryption of message 0 with R1, there's no way to tell whether these messages are the same unless these two random help values are the same. And if you pick the random help values uniformly from some large space, suddenly the probability of me being able to launch a successful attack by going through all of the possibilities is very small. So semantic security means I'm going to employ a probabilistic, well, in my case, semantic security means I'm going to employ a probabilistic encryption scheme where I use these random help values to hide the data inside. So now I've got something that I can encrypt with and isn't going to reveal anything by the fact that the ciphertext corresponds to something. Now, when we talk about auctions and finance, why do I care? Why do I want semantic security? We know we use it for Social Security numbers. Why do we need it for auctions and finance? Because we are encrypting bids. We're encrypting prices. And the space of a stock price might run between $0 and $1,000, even 100. What's Berkshire Hathaway now? $125,000 or something. So you're talking about 10 million possibilities for stock prices in pennies. You can run through those very quickly. So we need semantic security for that. The second problem now is one I alluded to where I took the ciphertext and I squared it. What I'd like to do is perform some operations on encrypted values. So we see with RSA we can do some funny things. Now, another thing we could do with RSA is so let's go back to RSA for a second, which we all know and love. If I have a message M1, which I've encrypted, and a message M2, which I've encrypted, and I multiply them together, what do I get? It's high school math, right? So I get an encryption of their product. Well, that's useful if I want to multiply encrypted values together. But say, yeah, question.
I'm sorry, maybe this is elementary, but people know about the
Sure.
confused. When you say that you're squaring the ciphertext, it's like you're not squaring the ciphertext. The ciphertext is m to the e mod n,
Right.
not m to the e.
Okay. This is a great question. So if you're not a number theorist, the notion that I can take this modular exponentiation, modulo n, and square it modulo n and get something that still makes sense is not intuitive. It turns out you can prove that in the finite field that is defined by so in the finite field of numbers that are relatively prime to n, which defines the space of exponentiations, that it turns out that the modular exponentiation operation mod n, if you square something mod n again, is equivalent to something over the integer operations kind of intuitively. The operation still makes sense. It's just that we wrap around sometimes. But if we take the decryption operation of RSA on this thing, it works out. Now, the caveat is if m1 multiplied by m2 happens to be larger than n, then you're going to get the value that is this mod n. So that also wraps around. This isn't a discussion of number theory. This is a discussion of these cryptographic tools. Did I say anything wrong? I'm looking at the mathematicians here. They're OK. All right. So multiplication, kind of useful, but we can do better than that. How many of you have heard of a guy named Pascal Pay? Great. So who is Pascal Pay? He was a PhD student in France who was working on cryptography, and he came up with an encryption algorithm that is a little bit similar to RSA in a couple of ways, but importantly different. And the Pay encryption function is I encrypt a message with a random help value, and I'm going to pick an n, which is some product of two large primes. And then I'm going to take n and square it. And I'm going to do my operations modulo the square of this thing. I'm going to pick a generator of the group. And a generator means that if I take the generator to successive x, if I multiply it by itself, it cycles through all of the elements of this group. So we pick a generator so that I don't, when I exponentiate, I am able to go through all the possibilities instead of wrapping around too quickly. So if you imagine, let's say I'm working modulo 10, which we think about, and I take the number 2, and I square 2, I get 4, and I square 4, I get 6, and I square 6, and I get 6, and I square 6, and I get 6, and I square 6, and I get 6, and this is a problem. So similar things happen when you're dealing with other products of two primes. 10 is a product of two primes. Or if you pick the wrong value, that in particular a value that is not relatively prime to the number n, you run into these problems. So I pick a generator, I exponentiate that to the message, and then I multiply it by my random help value r to the nth power, and I take all this modulo n squared. I'm not going to work out the number theory here, but let's look at the properties of this function. I'm going to ask you to take it on faith that this function has some security properties, because everyone else in the field takes it on faith that the decisional composite residuosity assumption underlying the security of this function isn't breakable. It actually hasn't been proven one way or the other. So me doing a lot of number theoretical proofs isn't going to really help, because I'll just prove to you that we still have this assumption. So I'm just going to ask you to assume a little more and show you the cool things about this function. So now I've got a function. Oh, for our audiences, I'm going to leave on this whiteboard. So now my encryption function is mr is g to the m, r to the n, modulo n squared. Now let's see what happens when we take two messages and put them together. What is this? Well, so notice that what happened with RSA was the messages were in the base. And here the messages are in the exponent. So what happens is G happens to be the same base. So instead of multiplying the base together, we add the exponent together. This is one of those cool things about exponents versus bases. So I end up with my generator to the power of the sum of the messages multiplied by the product of the random help values to the nth power. This is my ciphertext. So if I've got two of these, let's call this ciphertext 1 and this ciphertext 2, this is what? An encryption of, I heard it, say it loud, come on. M1 plus M2, right? So this is an encryption of M1 plus M2 with the random help value R1, R2. Sometimes I use random help values R2 and D2, but that's when I talk at Pixar. So now we've got something really cool. We can take two encrypted values that are reasonably secure, and using just the ciphertexts, we can take their sum. OK. And we can get an encryption of the sum without knowing what the plain texts were. So what can we do with that? Well, people have used this for voting. One of the first applications of this was I take a vote. Every candidate gets a different power of 2. And then I sum all the votes up at the end, and I can decrypt them. So it's just like bits, right? I've got, so my first bit, we'll call it 2 to the 0. And then maybe I have 2 to the 16, 2 to the 32, 2 to the 48. So if I have a base where each kind of bit is one of these values, and I get a 0 or 1 in each of these bits depending on the votes, I can sum up a vote for this guy, or vote for this woman, or vote for this horse, right? And I can sum many of them up to 2 to the 16th in any one column. And then when I decrypt it, I can then take the bits back out. But I have no idea, given any particular vote, what it was, if all I'm allowed to decrypt is the sum. So that's why this is cool for voting. But it's cool for other things which are not voting. So now let's talk about something like an add. Can I subtract? How would I subtract? Yeah. Divide? OK. So if I divide, and division in a finite field is simply multiplication by the additive inverse, right? So what I do is I take G to the M2, R2 to the N, and I raise this to the -1 power. And this gives me G to the minus M2, R2 to the minus N. And now I multiply this with that, and I get the difference. OK, so I can add and I can subtract. Can I multiply? Who says yes? Who says no? Can I multiply using an easy operation? Kind of. We can multiply by constants, right? We just did it. So it doesn't have to be a -1. I can take any constant integer, raise a ciphertext to that exponent, and get a encryption of this plain text multiplied by that constant. This is important. Say I've got, a stock price that's encrypted, and I know the number of shares. So I've got 1,000 shares of some stock price. I don't know the price, but I know the number of shares. So I can take the number of shares, exponentiate that, and then I get an encryption of the value of this thing, even though I don't know what the value of the stock is. But we can't directly multiply two ciphertexts together. Yeah.
Quick question about the subtraction.
Yes.
When you subtract and when you raise those to make exponents,
Yeah.
and you
You multiply it. Yep. No, you're retracting your question.
Yes.
Okay. Other questions? Yes.
This is also very elementary, but how do you do the decryption? Is the R end of the long loop message?
No. So the decryption is, I was glossing over it because it's a little messy, but the decryption is the same as RSA. If you know the factorization of n, you can efficiently decrypt by raising this to a power based on, so those of you familiar with number theory may know Euler's totient function, phi. So if I have phi of n, this is p minus 1 times q minus 1, which is the number of elements relatively prime to n. And in my space of exponents, I wrap around this many times because it's composite, not a prime. So when I decrypt, I raise this to a power based on this, and then because I know this value, I can eliminate how do I put this? I can eliminate out terms and end up with just the messages. It's a little messy. Go ahead.
So, just out of curiosity,
Yeah.
is this secure if you don't use R?
Is this secure if you don't use R? Let's say we used 1 for R every time. No. Why not? So if you, first off, if you use the same R every time, we'd have the same problem we had with Social Security numbers that Yasha mentioned, right?
Does this work like RSA?
No, it doesn't work like RSA because RSA is taking a message to an exponent. This is taking a fixed generator of the group to the message as the exponent. So it's somewhat different. Also, we're taking these things modulo n squared rather than modulo n. There are some important differences, but I really want to get into the meat of what this is good for, not the nitty-gritty of the crypto. So we can add, we can subtract, we can multiply by constant. Can we multiply two ciphertexts together? No. And if you can figure out how to do that, you could probably get tenure somewhere, because this is an important open problem to find a finite field in which you have closure under both addition and multiplication. It's sort of imagining two rings with a homomorphism between the rings, and then having two homomorphisms, both of which close, form closures. But I digress. A homomorphism, by the way, is this operation here, this multiplication operation, corresponds to this addition operation. So the space of ciphertexts, which looks like this, multiplied, has a homomorphism with the space of plain texts added. So that's what I mean by homomorphism, homomorphic cryptography. Don't be afraid of that word. So I can, however, not multiply them together, but I can prove to you that a new ciphertext, so let's say now I've got ciphertext C3, which is an encryption of another message times another random help value. I can prove to you that M3 is equal to M2 times M1 given, well, obviously if I gave you M1, M2, and M3, you could know that, but if I give you C1, C2, and C3, and you can look at the papers, there are various ways of doing this. So the point is, I can, in fact, do this. It's a lot more work. So what I have to do is use some fancy math to kind of, if you think about, remember when you were multiplying, polynomials in junior high algebra, x plus y and z plus w, and you use FOIL to multiply them together. You use a similar thing where you separate them into parts and then you multiply them together and prove that their sum is equal. And remember, over here we proved that I could take the sum of two ciphertexts and prove that that was equal. So when I multiply, I carefully craft a few special ciphertexts that we use to prove that the sums are equal. I'm not going to get into the details. Okay, so now what do I have? I've got addition, subtraction, multiplication. Can I divide?
Yes, no.
Division is hard, but again, since I can prove multiplication, I can kind of divide. I can prove division by proving to you that. Well, I can't directly do an operation that does multiplication, but I can prove to you. Yes, we can. I can prove to you that M3 is the product of these two messages, given only these three ciphertexts. But the whole point here is, here, I was able to calculate on my own a new ciphertext that was an encryption of the sum of these other two plain texts. And here I have to generate a new one and prove to you that it's an encryption of the product of the other two. And that's a slight difference. So with division, the way we do that is I prove to you that the result multiplied by one of the operands equals the other one. So if I say A divided by B equals C, well, all I have to do is prove that C multiplied by B is A, right? So since I know how to do this, I can also prove that. All right. So now, what else do we need? What else would we like to have if we're doing some arithmetic operations? So we've got the four basic operations. Comparisons, perfect. You read my mind or you read my papers. So comparisons, how do I prove comparisons? I'm going to start out with an operation that's somewhat simpler, and that operation is going to be prove that M is less than some constant K given an encryption of M, which we'll call a ciphertext. I can do this using these other operations. And one way that I do that that's very intuitive for you people, since you're computer people, is to separate M into bits. So let's think about this for a second. An encryption of M, let's say I'm thinking about, bids in an auction for a dinosaur. So I'll take bids in a charity auction for some dinosaur, right? So how much is this dinosaur going to be worth? Well, probably not more than $100,000, say. So now I'm talking about 10 million different possibilities. So what I'm going to do is, let's see, 10 million is 2 to the some power, certainly less than 2 to the 32nd, right? So now what I'll do is I'll have 2 to the 0. Okay, so I need 24 bits. Thank you. I knew someone would figure it out on their laptop or in their head, but I'm trying to give a presentation, and I'm not going to engage my brain for that. So now I'm going to come up with encryptions of all these bits. And encryptions of 0. And to represent any number between 0 and 2 to the 24th minus 1, I will select either an encryption of 2 to that power or a 0, and then at the end I'll sum them up. So if I were going to say, let's say M is 13, I'm going to take encryption of this, an encryption of this. So this is 1, this is 2, this is 4, this is 8. Encryption of this, encryption of this. So if I add these up, 1 plus 0 plus 4 plus 8, I get 13. And so I can prove to you that this encrypted message is equal to the sum of these 4 encrypted values. Yeah.
So, but to tell you which ones I chose,
Aha.
because then I know what the exact ones.
That's exactly right. So the question is, but you know, you're telling me that you're going to give me 4 of these encrypted values, and I'm not going to believe you unless you tell me what the values you've just encrypted are, right? So how do I get around this problem where I want to hide this by representing this as encrypted values, but not tell you what the encrypted values are. So the way around it is this cut and choose protocol. Who remembers what cut and choose? Craig?
Use it for birthday cake.
You use it for birthday cakes, right? This is where it comes from. So if you have two kids, two twins, and it's their birthday, how do you ensure that they both get equal sized slices of the birthday cake? One of them cuts and the other one chooses. And the cut and choose protocol is, we both don't want to, we want one person to do part of the operation and the other person to do the other half of the operation. So what we do here is a simulated cut and choose where I'm going to create a birthday cake of a very large number of sets of values. So I'm going to give you 100 encryptions of 2 to various powers and an equal number of sets of encryptions of 0. And I'll give you 100 of these little sets of encryptions. And then you're going to say to me, okay, Chris, decrypt 50 of them. But Chris, you don't get to choose which 50. I get to choose which 50. And since I've got to decrypt them according to your choice, Craig comes back and says, Chris, please decrypt numbers 2, 4, 7, all the way, of these 100. I give Craig the decryption, then Craig verifies that every one of those 50 sets that I gave him looks like this, is a set of 24 encryptions of 2 and 24 encryptions of 0. And I do that by revealing to Craig the random help values I used when encrypting these values. So that's why random help values are cool, among other reasons. But it is neat that you can decrypt either by knowing the random help value or by knowing the factorization of n. That's an aside. But it's important when we're verifying these test sets. I don't have to give Craig n. I can give him the decryption r for every one of these little things. So now I've got 50 of these things that Craig's never seen. But I know are correct, and Craig's going to believe me that they're correct because the probability that he happened to choose 50 of my 100 sets that were correct and the other 50 are incorrect and I'm somehow cheating is astonishingly small. And we can achieve an arbitrary level of security by changing that number 150 to a very, very large number if we want. So now I can prove that m is less than k, where, let's just call this 2 to the t. So this is t equals 24. I can prove that this message lies between 0 and some value. Do we believe that? Yes, okay. Some of you believe it, some of you are taking it on faith, that's okay. The point is that we can use encryptions of the various bits, use our addition operator to get an encryption of the sum of these bits. Now what? Well, what good is that? You asked me about comparing two encrypted values, not comparing a value to a constant. So back to some lower math, we'll call it. If I know that A is less than K and B is less than K, and I know that A is greater than 0 or equal to 0, what do I know about the relationship of A and B if I use one of these other operations? So now I have this, and if I also prove that their difference is in this range, what have I learned? Right. A is greater than or equal to B. I'm going to be pedantic because if A and B are the same, they could equal 0. And I could be giving you all zeros in my encryptions. How do I get a greater than operator if I have this?
Check that B is not greater than or equal to A.
What's that?
Check that B is not greater than or equal to A.
How do I check that B is not greater than or equal to A? I could do that, but that turns into the same thing as A is greater than B. So what I actually want to do, because I'm in a discrete space, is just say that A is greater than or equal to B And I know how to do that, because remember when I exponentiate it, you know, I can add a constant by multiplying b by an encryption of 1. So now I've got all my operations. I got greater than, less than, and greater than and equal to, and less than or equal to. So now I've developed all of these from this cryptographic framework. Okay. So why did they give me a doctorate? Let's think about auctions. Back to our $100,000 dinosaur. Everybody in this room is going to bid on a dinosaur that's going to go in a company courtyard. So, I'm trying to use examples that are close to home. When we get to stock prices, though, I'm not going to use examples close to home. We'll talk about arbitrary stocks. In an auction, how could I use this stuff? Well, I could use this because now I can encrypt all my bids up to, well, I'm already using N, so let's call it L. How do I prove to you who won the auction, given the encrypted bids? Yeah, so once I get all the bids, I can open them all up and look inside and see what the encrypted values are, and then I can pick the highest bid, and I can reveal to you which auction bidder was the highest by proving to you these operations on the ciphertexts. So I can prove to you, let's say bidder 2 is the winner. I show you that, the encryption of bidder 2, and I'm going to use this notation with the line through it to show that it's kind of bid 2 is greater than for all of the other bids. I'm going to show, in fact, that it's strictly greater than, we'll say there are no ties. All right, so why do we care about this? This enables an auctioneer, like the federal government, who does this, to conduct an auction where they prove who won the auction, and everybody who participated in the auction can look at the encrypted bids that were submitted to the auction and posted and verify that the encrypted bid of the purported winner is bigger than, represents a bid that was bigger than their bid. So everybody's satisfied that this person won the auction, but the government doesn't have to reveal how much the winning bid was for. Yeah?
Can't you just construct an encrypted bid for every value and compare the encrypted bid against it?
You could if the auctioneer were willing to help you do that. So the question is, could you construct an encrypted bid for every value and compare it? These operations are not something that anybody can do. These operations are things that I can prove to you, especially, so these are things you can compute on your own, right? You can compute an encryption of the sum or an encryption of the difference, but you can't decrypt that without the cooperation of the person who has the key. In these things, you can't even approach without the cooperation of the person who has the key. So the auctioneer is not going to prove to you facts beyond what is specified by the rules of the auction. So if this were an oracle that you could just go ask, here's my encrypted values, do this operation for me, then you could do the attack you specify, which is specify all the bids and ask for comparisons. But the oracle is smarter than that and is only going to reveal what the auction is supposed to reveal at the end. Yeah?
For the comparison, you need this fixed number K, right?
Right, so for the...
Tell me something about how large the gap to the second largest bidder is.
So the question is, I am dealing with a fixed constant for these comparison operations. And does that have anything to do with the difference between the bids? It would if I used a different K for each comparison, but I won't. So I'm going to choose a K that is big enough to accommodate every bid in the auction so that any difference is indistinguishable from any other difference.
But that does give away some information about the highest bid.
Right, so Craig points out this gives you some information that the highest bid is at most K minus 1. And so if you choose K to be arbitrarily large, that no one would possibly bid more than $1 trillion for a dinosaur, then you're okay. So that's what you do. You set K to be high enough that you can still efficiently compute it, but doesn't reveal anything meaningful about the bids in the auction. So the next step is, how many of you heard of a Vickrey auction? A Vickrey auction, yes, Craig has heard about it. You're Googlers, right? You know Vickrey auctions. Where does it come up? Don't you use it? Yeah, for AdWords. Ads, right? So a Vickrey auction is when you take the, what? Second highest bid. Okay, so how do I prove a Vickrey auction? How do I prove to the winner what they should pay in a Vickrey auction without revealing to anybody else anything they don't need to know? I take all the encrypted bids, and then I prove this. And then let's say bidder 3 is the second highest bidder, and now I prove that the encryption of bid 3 is greater than or equal to the encryption of bid I for all I is less than 2, I is less than 3. So I first prove the highest bid, and then I prove that this bid is greater than or equal to all the others, and then I decrypt this bid just for them by giving this bidder the random help value I used to encrypt this. They can verify the price is fair, and nobody else learns anything, except that the winner got the item. Yeah.
Oh, the winner got the item.
Yeah.
That was the question.
I mean, people need to learn that, right? You want to know that you lost fair and square if you're another bidder. Okay. It turns out that Vickrey pricing is even more complicated than just second price. In some contexts, the more generalized Vickrey auction computes what the... So imagine now, instead of auctioning off a dinosaur, I'm auctioning off $1 billion worth of treasury bonds. And not anybody is going to buy all of the bonds that the Treasury is auctioning off. They're going to buy a certain amount, and they're putting in interest rates in their bids. And the people with the lowest interest rates are going to win the auction. Right? The people who are going to charge the government the least will win the auction because the government wants to pay as little interest as possible, theoretically. So in that case, I've got an auction of many items, all of which are identical. In a generalized Vickrey auction, I prove that the price that a bidder pays is the price that they would pay, is the price that the winner of their items would pay if they weren't in the auction at all. So in a bond auction, the person with the lowest interest rate, the most competitive bidder, you imagine the auction without them and figure out what the lowest interest rate would be without them, and that's what their bid is. And so in the papers, we actually develop, using these operations, an accurate generalized Vickrey auction pricing, so we can actually compute and prove correct the prices that everybody pays at the end of the auction without revealing to them anything about the other bids beyond what is implied by the bids. So you can imagine in a Vickrey auction with discrete bids, someone proving to you that you are, that your bid is this and your payment is this other thing. You could do some linear programming to figure out what some of the other possible bids would be. But you would know that anyway if someone told you what the price you had to pay is. So all we prove is what the price we tell you is accurate. So this is how we use these operations in auctions. There's another approach, which is not in auctions at all, and this is an important part of my doctorate. So I came up with this idea of what I call a cryptographic securities exchange. And a cryptographic securities exchange is like a continuous double auction. Tell me if this whiteboard is legible. Those of you who have the please zoom on whiteboard, you can go right on that if this is not legible. So A cryptographic securities exchange is one where I have a limit order book, and those of you with vested stock options probably know what a limit order book is. It's a set of prices that people are bidding for and asking for a particular stock on an equities market. Now, a problem is if I am in a stock market and I want to sell 1 million shares of XYZ Corporation, and I go to the market and I say, okay, sell 1 million shares at the market price, what's going to happen? Price is going to drop, right? Unless there's somebody who wants to buy 1 million shares at the current market price, I'm in trouble. So I don't want to just go sell at the market price, a huge block order. All right, so I'm selling some XYZ. I go look at the limit order book. I go place an order. I'm going to sell, well, 2030 is the best price, so I'll sell my 1 million shares at 2029. Now we can play the Sesame Street game of which one of these is not like the other. And if you were looking at XYZ stock and you saw this limit order book, what would you tell me? This is unbalanced, right? There's something wrong because all these other orders at various price points are much smaller than this 1 million shares that I'm trying to unload. And it turns out that on Wall Street, people take advantage of these kinds of orders. Block trades, when they leak, reveal intentions of people buying or selling, and people will do something called front running sometimes, which is I learn about an order that someone's trying to unload a big block of stock. I run in front of them to the trader, and I sell before they do. And when I sell, let's say I short sell, I borrow the shares, sell them, then their trade depresses the price, and then I buy back at the lower price. Another form of this is something called penny jumping, which is, gosh, I see this order for 1 million shares. Why don't I, make an order for 2028? So I'll sell some shares. Maybe I'll sell 10,000 shares. And if I assume a distribution of stock prices that's kind of random, the chances that the price will go down after my order gets filled before this thing gets filled is high. And if I can make 3 or 4 pennies on my transaction, I've just made $300 or $400 minus commissions. So what happens if the price goes up? Well, the price goes up, but they've got to eat through this gigantic order, and so by the time this order gets eaten through, I'm going to notice, and I'm going to buy back my shares from them, rather, before the order is filled, and so my downside risk is limited to a penny, but my upside risk is not that limited because the price could go down a lot more because I don't have this big, what's called a free trading option sitting here on my limit order book. So my solution to this was, well, let's encrypt the bids and the asks. Let's encrypt the prices and maybe even the quantities so that people don't know what's going on in the market and they can't exploit it. So how do I do that? Well, I know how to encrypt values already, so I'm going to take my encryption function and I'm going to encrypt all of these things. And now, all I see is encrypted values on my limit order book, and I don't know if you're selling 1 million shares or 5,000 shares. How does it work? Somebody comes in, they give the market their encrypted order. The market operator comes in and says, well, okay, I'm going to erase some of these. So now I come in with my order for 1 million shares, and I don't know what the price is. So say I come in and I put an order to sell 1 million shares. Let's buy. So I'm going to buy. Let's say I'm going to buy 100,000 shares at $20.33. So what happens? These values are encrypted, these values are encrypted, but I can prove that 2033 is greater than 2030. I can prove that it's greater than 2031. So even if the prices are encrypted, I can prove to you that these orders sitting in my encrypted book that I've been publishing should be filled by your order. And I can prove to you that your price is less than 2035, so this one shouldn't be filled, and that the rest of these shouldn't be filled. So then I fill the sum of these two quantities, and I can compute the sum of the quantities with my addition operation over there. And then I can leave a new order on the book. So I cross these off, and I add a new order on the book for $20.33 for 100,000 minus 1,700 minus 2,000, which is just an encrypted value I can calculate by using these other encrypted values. So, okay, this is kind of a neat idea. But in the remaining 5 minutes, I want to talk about even going beyond this, and this is because this is just for one equity. So you can imagine this could be useful a little bit for block trades of a single equity, but it turns out on Wall Street, most of the asset management, most of the asset trading that is done is not just people investing in single equities, it's people investing in portfolios of equities that have some correlation with each other. So to do well, if you're, say, David Swenson at Yale, who's been outperforming the market for many years, he uses portfolio theory and the correlation of various equities to figure out portfolios of equities that are likely to do well in the future based on how the ups and downs of the individual equities correspond to each other. Okay, so if I've got a portfolio of equities, now I'm just using ABCDEF, I don't want to talk about any particular one. Now, and maybe can we zoom the video in on this for the remote people? Great. So now, what's my problem here that I can solve? Well, over here what we were solving was people putting in orders and that order information being exploited. Over here, the problem is, let's say I want to sell you my portfolio. And because I've done all this portfolio theory work to get a portfolio that's well correlated, I don't want to sell you 6 different equities at different times. I want to sell the whole thing at once. Because let's say I sell you A now and D later, and look, I've got 1,000 long of this and 2,000 short of that and 1,000 short of this. If I sell all the longs at the beginning, and then 2 hours later I don't get my short fills until then, suddenly my portfolio becomes unbalanced and I have market risk. So I've done all this work to get a balanced portfolio, but when I'm trying to sell this portfolio, I need it to be traded atomically. So I'm going to go to Antonio and say, hey, Antonio, you want to buy my portfolio? And Antonio says, well, what's in it? And I say, well, I can't tell you, because if I told you, you could front run me. So remember, we've just talked about how if you know about trades coming up, you can front run them. So how do I tell Antonio what's in my portfolio without telling him what's in it? What I can do is give him risk characteristics of my portfolio that he might use in his risk management software, that he might think about in hedging, in understanding what he's taking on, by saying, okay, what's the average market cap of the equities in my portfolio? So now let's say these quantities are encrypted. Now, all we need to encrypt are the quantities, because everything else is public. Last price, the closing price yesterday or the current market price, that's public. The market cap is public. That's just the outstanding shares times the price. The sector is public. Obviously, the name of the equity is public. So if I encrypt the quantity of all my equities, then I've got an encrypted basket, an encrypted portfolio, and I can prove to you the average market cap by doing what? Well, I take now I probably want to do this value weighted, so I take the price times the quantity times the market cap, right? Remember, I can add and multiply. So I take the price times the quantity times the market cap for each of these things, and I end up with an encrypted product for every one of these, 4, 5, 6 of them. Add that all up together, divide by 6, and then I reveal that encrypted value to you so that you don't learn the price or quantity of any single thing. You learn the average market cap. Now, I'm cheating a little bit here because this is a short position, not a long position. And if I used negative 2,000 directly, we'd end up with problems. So I'm going to assume that we can either have an absolute value function, which I skipped, or that you use a bit for positive or negative plus the quantity. If I wanted to prove to you what percentage, I'm almost done. If I wanted to prove to you what percentage of these were in the telecom sector, I could do that by proving to you the entire value of the portfolio, and then proving to you the value of this, and then taking the difference, but you wouldn't know anything other than the percentage. So I can take this times this, and this times this, or this times this, which is this. So I have 50K of this and 80K of this. I can compute the encrypted value of the entire portfolio, which is minus 50K net, or let's see, 130, 200, 330 plus 300. So this is the net, and this is the total notional value. So I can compute these encrypted values and divide the value of any particular sector by adding the components up and dividing by the total, right? So the point is these cryptographic tools enable us to do things in auctions, risk analysis, and financial trading that are pretty remarkable. We can control who knows what. We can control, in fact, how they know, when they know it, which is another talk. Some of the research that I worked on involved sending a message into the future. So you can look on my webpage. There's a paper called Time-Lapse Cryptography by Michael Rabin and myself, where we discuss a way of encrypting a message so that it's guaranteed to be revealed in the future, but secure until then. There's other things you can do with this. For example, I could say, I've got this portfolio and another portfolio and a third portfolio, and I'm going to combine them together to get a final portfolio, and then tell you the risk characteristics of this combination of 3 portfolios. So you could imagine a financial exchange for portfolios that, rather than people trading individual equities, you actually put in portfolios, and this exchange would tell you the risk characteristics of all the portfolios that people want to trade, and then people could bid on little chunks of that. So hope this was interesting. I wanted to give people a taste of these, simple cryptographic tools and the kinds of amazing things you can do with them when you apply it to one area of finance. There are a number of other areas that I think these crypto tools would be useful for, and that's why I came to Google, because here you come with an idea and you say, well, I have this idea for this tool, and here's how I use the tool. And someone at Google will say, well, that's an interesting tool, and I understand how it works for that, but we could really use it for this other thing. So I'm going to stick around. I hope that some of you will tell me and ask now ideas that you have for how these tools might be useful in other applications, and ask any other questions that come up. Thank you. For questions, or hopefully there's some questions, or I left everybody behind. So I'll even throw the microphone to you if you don't want to get up.
I have a question.
Okay, question.
It seems to me that interactivity is essential for this proving for the auctions.
Yes.
And is there any way to reduce that or avoid that?
So the question is there a way to eliminate the interactivity? Can you do this in a way that's autonomous, that's sort of, you don't need this third-party who has the decryption key who's proving these facts to you? The short answer is no. And if you think about a system that isn't interactive in some way, how would you prevent people from learning too much? So if you don't have a third party who's kind of the gatekeeper and complies with the rules, then how do you, because imagine that I have this oracle that proves all these facts, right? If the oracle has no rules, then I can just ask it a bunch of questions and learn everything that I want to know. So you need a third party who has the keys so that the information stays secret and selectively reveals only those things that should be revealed. And so you kind of need the back and forth of parties taking their information that they want to encrypt, encrypting it, sending it to a third party, and then the third party revealing the results of this computation to somebody else.
They also bring more of the sort of zero knowledge proof that's going on with the less than operation.
Okay.
So it seems that's the only place where you actually have an interactive proof in the sense of a zero knowledge proof.
Right. So in that case, you can get around it by not doing an interactive cut and choose protocol, but you could use like a Goldwasser-Macaulay technique of doing a hash. So you could take all of these. Let's say I give you 100 test sets. We hash them using SHA-1 into some hash value, and then we agree beforehand on a function that takes a hash value and transforms it into a permutation of the various test sets that defines which of the test sets I have to reveal. So you can do it that way. So you can make it non-interactive in the same way that some of these other zero-knowledge proofs have been made non-interactive, which you take the inputs, use a deterministic but hard to invert hash function on the inputs, so that the output is all deterministic. Does that answer the question?
Yeah, sure.
Other questions? I'm really eager to hear Googler's perspectives on what this could be useful for. I mean, this is stuff that I've said, well, this could be useful in financial markets. I could hide stock prices. I could hide auction bids. But are there things where we could hide integer data and perform operations on them that you guys are thinking about that I haven't really thought of before? Would this be useful in AdWords? I don't know. Do advertisers care? Or do advertisers just trust you guys to not be evil and give them fair prices? Yeah. So, in these cases where people are paying a nickel or, a dime or at most a couple of bucks, right, for AdWords, we're not talking about billion-dollar wireless spectrum auctions where people really do care about the outcome. No, I mean the outcome of the auction. So if the advertiser is less likely to worry about, I think an advertiser for an AdWords campaign is less likely to worry about being overcharged in an auction by Google, in part because of Google's reputation trust, and also because it doesn't seem like there's a lot of opportunity for fraud there in the way that there is in, say, a wireless spectrum auction, where if I'm the government and I get one of the bids early, or I learn something that I shouldn't, I can transmit that information to one of the other bidders, and that can have a really measurable difference.
Like the advertiser could just stop using Google.
Right.
I mean, the auction is more a tool we use to get a good price, right? But they
Right.
don't really have to understand how it works.
So yeah, that's a good point, right? The auction at Google is used for price discovery, and it's not used for revenue optimization in the same way.
I think the biggest barrier for something like this is that the proofs are pretty opaque
Yep.
to most people. I think that we just move the problem of not trusting rules, not trusting the verification of it.
Okay, so your point is, for the general public, you can give them these mathematical proofs, but unless you have a PhD in computer science or number theory, maybe the proof is a little opaque and you don't believe it anyway.
Right, you don't understand it.
You don't understand the proof, and so you have to take it on faith that the proof makes sense, and who do you trust?
We
Yeah.
have the same problem for SSL, right? The conservative knows that SSL is safe.
That's right. You can trust that the person who implemented SSL, which is the browser,
Yeah.
has no reason to fake it.
That's
or
true.
find it.
Right.
So,
And so that gets into one of the other things that I've discussed, which is you kind of want a third party who isn't interested at all in this stuff and just makes it his job to do these provably correct computations. So you ship your computations off to this big cluster of computers that do your math and prove the result correct, and they don't care what the computation is.
but they need to know some information like in order to be able to do some of these comparisons.
They just need to be able to decrypt. Yeah, that's right.
So yeah, I was going to say that an area that would be really exciting, right, is cloud computing, right? To be able to make use of a service, right? Maybe even run my own script on this service. I'd like to know that they didn't tweak anything, right? That they actually ran the script exactly as I wrote the script, without having to do all the computation myself. Does this lead to that, or is there still barriers?
So there's a couple of there's two things going on, and I'm going to answer it in two ways. The first question is, does this lead to provably correct computation where I ship my inputs out to the cloud computer, and the cloud computer computes the result and proves the result is correct to me? It turns out that this machinery is more than you need for that. And that's because if you don't care about the cloud computer revealing your inputs to somebody else, or you don't care about the security or the secrecy of the data, and all you care about is the correctness, then what you want is a language that allows you to define a computation and then define a correctness proof. So let's think about this in a very simple case, the PNP problem. I'm joking when I say it's simple. So the whole debate about P equals NP is, can I take a hard problem like, here's a map, compute the traveling salesman problem over this map, and give me the output? Or here's a map, please color all of the states on this map using one of three colors and give me the map back. Now, in some cases, like the three colorability problem, I hand this off to the cloud computer, and the cloud computer either comes back with a correct answer or not, and I can verify that the answer is correct efficiently. So there are some classes of problems for which the evaluation of whether your answer is correct or not is computable in polynomial time when doing the computation is not. And in those cases, it's related to this work because we kind of talk about it where we say, well, the whole point of having this third party is not just to do the computations, but also in the case of combinatorial auctions, which I didn't cover, which are far more complicated, where people are bidding on many things at once and buying many things at once, proving the optimal result. In that case, proving it correct can be more efficient. You can have this giant computer spit out the result, and then you can prove it correct. And in our case, we can prove it correct using these encrypted values so that you can prove to all the bidders who won or lost. And the cloud computer doesn't have to reveal all of the results of the computation. They can reveal the encrypted results, and those encrypted results can be verified. So it's related in the sense that there are many cases in which a cloud computer would be one of the only feasible ways of computing the optimal result for a complicated auction, and you'd want proofs of correctness, but the encryption is orthogonal to those correctness proofs. So the encryption doesn't really help, but the correctness proofs do. I am not an expert in provably correct computation, and so I would say, if what you want to know is, how do I prove the result of my computation was correct off of this giant computer, there are classes of problems like three colorability that are in NP that are easy to do, but there are other classes of problems that are harder than that, for which, say the computer comes back and says, I can't find an answer, sorry. There's no three-color ability. There's no way you can three-color this map. How does it efficiently prove you that fact? Right? So, and I don't have a ready answer for that. This is a hard problem that I think is a really interesting one you guys are dealing with. What other questions? Okay, well, if you don't want to ask a question in front of everybody, come up after and I'll hang out.